The standard CT workplace is divided into two functional areas, the scan room and the control room. The scan room contains the computer tomograph machine. The control room is separated by a radiation protection wall and consists of the radiographer's workplace with the acquisition workplace AWP and the control box, and may contain additional workstations for image post-processing. These add-ons depend on the specific design of the CT facility and might, for example, include a CT workplace or a Singo-Via workstation. This chapter will introduce you to the system components of a CT scanner, with a special focus on the X-ray tube and the detector. Two scanning advancements, made possible by modern detector design, will be described: multi-slice scanning and acquisition modes. The computer tomograph consists of a stationary and a rotating part. The rotating part contains the X-ray tube, detector, several filters and fans, and electronic components, for example, those associated with the data transfer. The stationary part includes further electrics, connections for power supply and cooling, and, for some scanners, the tilting mechanism. The patient table, also called patient handling system, is mounted in front of the gantry. One of the main parts of a computer tomograph is the X-ray tube. The tube produces the X-ray photons after it is energized by an electrical current. The energy level of the photons is determined by the voltage value. This kilovoltage has a significant impact on radiation dose and image quality. To be more specific, the tube voltage determines the X-ray spectrum. The chosen kV value defines the maximum energy of the photons. When the tube current is kept constant, an increased voltage leads to increased penetration capacity of the X-ray photons, increased dose, reduced image noise, and reduced low-resolution contrast, for example, in soft tissue. The detector is located on the opposite side of the X-ray tube. It is the other main part of the computer tomograph that is incorporated into the rotating gantry. The detector converts the X-ray photons into digital data in several steps. First, the collimator, made of tungsten shielding, suppresses scattered radiation. Second, the ultrafast ceramic detector, UFC, converts X-rays into visible light. Third, the photodiode converts visible light into electrical current. And fourth, the analog-to-digital converter transforms electrical signals into digital data. The first scanners were equipped with a single-row detector. This means one image is acquired in each rotation. Nowadays, all CT scanners have multi-row detectors. That means multiple images are acquired during a single rotation. This may lead to a reduced scan time and results in the following advantages. A shorter breath hold is required, and fewer motion artifacts occur. Furthermore, multi-row detectors enable multi-phase contrast-enhanced scanning. Depending on the detector design, different acquisition modes are possible. For most examinations, the full detector size is used. But for some special examinations, only a part of the detector is used for data acquisition. For example, in neuro mode. This avoids geometrical distortion, especially for tiny objects. With the smallest element size of 0.6 millimeters, a thinner reconstruction is possible. For example, with a slice thickness of 1 millimeter down to 0.6 millimeters. This chapter will address the functionality of a CT scanner. After covering the basics of the image generation process, it will discuss sequential versus spiral scanning and the automatic adjustment of the scan parameters using the sure view concept. During the CT examination, the X-ray tube and the detector rotate around the patient in the gantry. Rotation by rotation, axial slices of the body are captured one at a time. The sequence of the image generation steps is as follows. The X-ray tube generates the radiation. The rays penetrate the body and are attenuated by the tissue. The attenuated X-ray beams are processed by the detector. The detector converts the radiation into electrical signals, and the computer converts this digital data into high-resolution images. The image generated by the CT scanner is a digital image and consists of a square matrix of elements called pixels, each of which represents a voxel, that is, a 3D volume element, of the patient's tissue. Sequential scanning is an incremental, slice-by-slice imaging mode without table movement during data acquisition. This scan type results in interscan delays between each acquisition, caused by the movement of the table to the next slice position. With multi-slice CT scanners, sequential scanning is performed using different combinations of detector rows and slice collimations. Therefore, one or more slices at different slice widths can be constructed from a single multi-slice sequential acquisition. The interscan delays prolong the scan times. Another disadvantage is that sequential scans are prone to slice misregistration. This is caused by scanning at different respiratory levels. Thus, common routine applications of sequential scanning are limited to head and spine imaging because the motion artifacts in these regions are minimal. Most other routine and advanced CT examinations are typically performed using the spiral scan mode. Spiral scanning is a continuous volume imaging mode. Data acquisition and table movement are performed simultaneously for the entire scan duration. A typical range can be acquired in a single breath hold. Each acquisition provides a complete volume data set, from which images with overlapping slices can be reconstructed at any slice position. Compared to sequential scans, spiral scans offer the following advantages. The examination can be completed within one breath hold. Shorter scan times facilitate the reduction of motion artifact and lower the need for contrast medium. There is a better differentiation of contrast-enhanced phases, for instance of arterial and venous phases. It is a better method for 3D reconstructions when scanning restless patients. The pitch is a spiral scan parameter that determines the speed of the table movement and the speed of the acquisition. The higher the pitch, the faster the table feed, and the shorter the scan time. Generally, the pitch for single-source scanners is between 0.35 and 1.7 and can be selected with an increment of 0.05. When increasing the pitch, the tube current, that is, the MA value, must also be increased to obtain the same image noise or dose. This is done automatically with the so-called sure view concept. Due to the effective MAS, the pitch factor no longer has any influence on the image noise because MA is automatically adjusted according to the pitch. The tube current is adjusted to the table feed in the following way. When the table feed is high, higher tube current is applied. When the table feed is low, lower tube current is applied. This chapter focuses on a set of essential parameters that are involved in the reconstruction of high-resolution images from the detector-generated digital data: field of view, convolution kernel or short kernel, slice thickness, increment, CT number, and CT window. The anatomical area displayed within the CT image is called field of view. The dimension of such a CT image is determined by the matrix size. The spatial resolution can be generally improved by using the smaller field of view because it reduces the pixel size. However, images should always be reconstructed with an appropriate field of view that is adjusted to the anatomical structure of interest. Thus, the visual impression can be improved without overmagnification. The field of view is limited by the maximum size of the scan measurement fields. Generally, you can reconstruct a maximum field of view of 50 centimeters for the body and of 30 centimeters for the head. To improve the spatial resolution, the field of view should always be tailored to the object of interest. That means it should be as small as possible. But take care when defining the field of view, because significant findings may be excluded from the images and missed during data interpretation. Usually, the first reconstruction is done with a large field of view as an overview, and additional reconstructions are done with a smaller field of view according to the organs of interest. For example, only one of the lungs or single vertebras. The convolution kernel or short kernel is a reconstruction parameter affecting image sharpness and noise. The kernel applies a specific mathematical algorithm that digitally filters the raw data during image reconstruction. The image sharpness is defined by the numeric values in the kernel name. The higher the kernel number, the sharper the image, but the greater the image noise. The letter after the number indicates the scan mode. S stands for standard mode, F for fast mode, and H for high-resolution mode. The kernel concept changed in 2013 for Siemens Healthineers CT scanners in the Samaras 5 and 7 groups. And on all systems going forward, an updated kernel labeling system will be used. The first uppercase letter stands for the kernel family. The second lowercase letter stands for the kernel group. The resolution, which refers to the image sharpness, is defined by the subsequent number. The overall principle is the same as before. The higher the number, the sharper the image impression. The parameter slice thickness, also known as slice width, describes the thickness of the reconstructed images. Slice width should not be confused with collimation. However, for single-slice CT imaging, these terms are regarded as synonyms because in this case, only images with a width equal to scan collimation can be reconstructed. With multi-slice CT imaging, the possible slice widths depend on the chosen collimation and scan mode. Several slice widths can be selected post-acquisition by combining data from the various detector rows to reconstruct the axial images. A narrower reconstructed slice width results in improved axial resolution, but also increased noise. You can see the effects in the images on the right side. Increment is the distance, in millimeters, between the reconstructed images in Z direction. It can be freely adapted from 0.1 millimeters upwards for spiral or 3D sequential scanning. If the increment is smaller than the slice width, the images are created with overlap. This provides better detail of the anatomy, as well as high-quality 2D and 3D post-processing. For routine 2D viewing, image series with contiguous increment are typically reconstructed. This reduces the total number of images for documentation and archiving. The CT value is used to represent the mean X-ray attenuation value of the corresponding volume element, or voxel, within the slice. CT numbers are normally expressed in terms of Hounsfield units. The CT number scale is defined so that water has a value of 0 Hounsfield units. Denser substances are given positive values, and less dense materials negative numbers. Normally, CT values are measured in the range from minus 1024 to plus 3071, with values around minus 1000 Hounsfield units representing air, and the highest numbers corresponding to very dense material such as bones. Since the human eye is only able to distinguish approximately 20 gray tones, it is not practical to always represent all possible Hounsfield units in a single comprehensive grayscale. Therefore, the parameter CT window limits the image display to tissue of interest. This results in a better differentiation of tissue with similar densities. All pixels with values above this range are represented in white, and those below this range in black. The window center, also called window level, and the window width define this range of CT numbers displayed in grayscale. The last chapter of this training is dedicated to the important subject of radiation dose. It gives you an overview of the exposure to background radiation and the dose considerations applying to CT procedures. Furthermore, it explains patient dose parameters and provides dose definitions for the absorbed, equivalent, and effective dose. Humans are constantly exposed to natural radiation, cosmic and terrestrial. This dose varies, depending on the location, between 1 and 6 millisieverts per year, with an average of 2.4 millisieverts per year. If the artificial radiation by medical imaging procedures and human nuclear activities is added, the average radiation dose received is about 4 millisieverts per year for German and about 6.2 millisieverts per year for U.S. citizens. Computed tomography is a very valuable diagnostic tool, and it provides much more information than a conventional radiograph. However, the dose in CT can be much higher compared to conventional examinations. Therefore, it is important to limit the patient dose by using dose reduction techniques and applications. For example, care dose 4D. Patients should not be exposed to excessive irradiation, and the clinical indications must be verified before performing a CT exam. The common practice is to apply the ALARA principle, where ALARA stands for as low as reasonably achievable. The aim of ALARA is to minimize the risk of radioactive exposure to a level that is necessary to obtain the desired diagnostic information. We all have an intuitive understanding of what dose is, but a radiation dose that reflects the potential damage to organic tissue cannot be defined simply as a certain amount of radiation energy per kilogram or square centimeter of body surface. That is why 3 different definitions are used: absorbed, equivalent, and effective dose. The energy dose or absorbed dose, D, characterizes the amount of energy deposited in matter after being exposed to a certain amount of radiation. However, this physical definition is not suited for living organisms, since it does not reflect the biological effects. The type of radiation and the damage it might cause in different tissues have to be taken into account. The biological damages caused by different types of radiation are not the same. Therefore, even if an absorbed dose of X-rays or alpha rays is similar, the damage can be dramatically different. The equivalent dose, H for any type of radiation, is defined as the absorbed dose, D, multiplied by a factor, WR, that weights the damage caused to biological tissue by a particular type of radiation. In the case of X-rays used in CT, the weighting factor is 1. Therefore, the equivalent dose is the same as the absorbed dose. In the case of alpha rays that occur naturally and are emitted, for example, by some types of uranium isotopes, the absorbed dose has to be multiplied by a factor of 20. This indicates that alpha rays cause much more damage to biological tissue. In radiology, the term dose or patient dose is always related to the absorbed dose, a measure of the energy deposited in a patient's body by ionizing radiation. There are 3 main quantities that describe the patient dose in CT: CT-DI volume, the volume CT dose index, DLP, the dose length product, and effective dose, E. The CT-DI volume describes a local dose or dose density, energy accumulated per mass. Contrary to common thinking, the CT-DI volume does not change when the scan length, the coverage, is increased. However, the DLP and the effective dose values actually do take the scan length into consideration. They are more consistent with the general understanding of the patient dose. The CT-DI volume is a measure of the dose absorbed during a CT examination. It is a local quantity describing the energy deposited in a unit of mass. The CT-DI volume is calculated from the integral of the dose profile produced in a single axial scan, corrected for the weight of the patient and the pitch factor. The CT-DI volume gives a good estimation of the average dose applied in the scanned volume, as long as the patient size, that is, the cross-section, is similar to the size, that is, the diameter, of the respective dose phantoms. Since the body size can be smaller or larger than the 32-centimeter plexiglass phantom, the CT-DI volume value displayed can deviate from the dose in the scanned volume. The product of CT-DI volume and the length L in centimeters of the scan range is called dose length product, DLP. In order to calculate the total absorbed dose for a complete CT examination, the scan range that is being examined must be taken into account. The dose length product is measured in milligray centimeters. Because DLP takes into consideration the geometrical extent of irradiation, it is considered to be a better indicator of the patient dose than CT-DI volume. It describes the total energy deposited in the body. Therefore, it is often kept with the patient record. When multiple series are performed, the DLP value for all series should be added to obtain the total DLP, which reflects the total dose for the entire examination. With the use of specific organ-related factors, DLP can be used to calculate the effective dose. The weighted average of organ dose values for the irradiated organs is defined as the effective dose, E, expressed in millisieverts. It describes the stochastic radiation risk. The organ dose is the product of the average absorbed dose in an organ, multiplied with a weighting factor. This factor indicates the effects of the different types of radiation, such as X-rays or ionizing neutrons. The effective dose can also be estimated by multiplying the DLP with a conversion factor determined from measurements or computer simulations. The conversion factors, F, are reported by the European Commission. The calculation of E using Siemens default protocols depends on the CT source.